I'm Chuck Lukaszewski. As Tom said, I'm in the CTO team at Aruba Networks, and I own what we call the wireless strategy portfolio. So I look at what we should be building, essentially, beyond the products that we're committed to building and shipping in the next sort of year and a half. And I own our standards team, who is active in IEEE and Wi-Fi Alliance. I also, in the last 2 years since we became part of Hewlett-Packard Enterprise, have taken on a new function that we really weren't involved in previously, which is policy and regulatory advocacy. And that's really what I want to talk to you about today, which is the new spectrum that is in play, which is an incredibly exciting development. It's probably one of the most significant developments to happen to Wi-Fi in certainly 15 years and 30 years, depending on how you count. So we're going to talk about basically 5 different topics. We'll start with, okay, why 6 gigahertz? And just out of curiosity, because it's been in the news lately, how many folks here have heard about a new band for Wi-Fi? Okay, good. So very topical, and as if I can't claim credit for this, but we got a draft notice of proposed rulemaking from the FCC, which I'll be talking about. When we originally scheduled this talk, we wouldn't have known that it was literally coming out the week before I was speaking, but the timing is really good. But the other thing I want to do is I'm going to walk you a little bit through the process of how a new band gets open, because this doesn't happen very often. The last time this happened in the US was about 20 years ago. And so history is sort of being made in some sense, and you all do different things, and you take advantage of the technology on a day-to-day basis. But I want to give you a little bit of a peek behind the curtain, because it's been new to me learning how to do it, and I'm privileged that Aruba actually has the resources to sort of engage on this at a global level. So I'm going to walk you through some of the key steps, and then we'll close talking about essentially what the position of the Wi-Fi industry is that we've taken with regulators, and then a little bit about where the FCC has come down with the draft item that they're going to be voting on the 23rd. So let me start by just giving you kind of a quick landscape of what we're dealing now with now in the 5 gigahertz space. So 5 gigahertz is effectively built out, and I have an asterisk because you always have an asterisk where spectrum is concerned. And as you can see from the diagram, there is a question mark on the right side of the diagram. But this is what you're looking at is basically a spectrum map of the US and Canada, and then a selection of other major Wi-Fi economies. And you can see the channel availability. We still have a lot of work to do on harmonization, which is the word that's used in the regulatory world for just getting the rules aligned. You can see that pretty clearly. But what I want to call your attention to is the big block of red in the center, and then the big block of red on the right. So the last allocation of spectrum for unlicensed was done by the ITU in 2003, so there's literally been nothing since then. And by the way, that took about 5 years to get done. The work for that really started in 1998, so it's been almost a generation. In 2013, the FCC initiated a proceeding to open up essentially the entire space that you're looking at. But we found out a little over a year ago that there's a national security application in Uni 2B that is simply not surmountable. And so that is off the table globally. So we were really counting on that to sort of fill in the gaps from an 80 megahertz and 160 perspective. And then on the right side, this is the DSRC, or it's Intelligent Transportation band, which has been stalled for a number of reasons we don't have time to get into today. So, there's an asterisk on that because actually the National Cable Television Association just filed earlier this week that they want to sort of reopen that proceeding. So anyway, if this is the 5 gigahertz landscape, you can, to use a zoning metaphor, right? We basically 5 gigahertz got zoned into these blocks, and then we've been building it out for the last 15 years. So where are we going to zone next? And so that's where 6 gigahertz come in. But before we get to that, why do we need a new band in the first place? well, you work with the technology every day, you support networks, and you're kind of on the front lines. But I would tell you that our entire business, both from our perspective as a vendor, from your perspective, I know we have a lot of different people in the room here, consultants and end users and vendors and so on, but we all take the spectrum that we depend on for granted, right? Because it got done for us 20 years ago, and we really haven't had to worry about it, right? It's just kind of there. But if you think about what the cellular industry goes through with each new generation, right, and the amount of money that they spend on spectrum, it's not free, and it doesn't, there is no technology has an inherent right to a band. So, and beyond that, it's controlled by other people, right, namely national regulators, and it takes a long time to open a band. And given, if you're following what's happening with LAA and the LTE technologies, 3GPP technologies, it's important that we have enough spectrum to keep up with all the new spectrum that's going to be allocated for 5G. The next reason is that the Wi-Fi brand promise is actually stalled, I would say. So how many people here, just out of curiosity, turn off 80 megahertz channels and are running 40s or 20s as a common deployment technique? Yeah, okay, that's my point, right? So we don't have enough channels to really get a repeating channel plan, right? So for co-channel reasons and stuff you guys understand. So on the one hand, we're pitching that we can do multi-gigabit rates, but on the other hand, the first thing you do when you open the box is defeature the product. So from my perspective, that's unacceptable, and given the exponential increase in the loads that are coming to us, the solution is more spectrum. And then finally, of course, 5 gigahertz is beginning to show strain, and it's isolated, it's specific use cases, right? It's multi-dwelling units, it's residence halls, airports, and so on. It's, depending on what studies you look at, we're carrying 60 to 80% of all mobile traffic, depending on which country you're talking about. And then, of course, LAA is deploying. There will be on the order of 3,000 or 4,000 LAA nodes in the United States by the end of this year. We expect it to be mostly outdoors, but there'll be some indoors overlaid as well. And so we are not the only technology in the band that's providing high bandwidth applications. So how much more spectrum do we need? The Wi-Fi Alliance did a study came out in February 2017. What this is showing you, the two colored bars on the left are a 2020 estimate, average and high. The right two bars are 2025, and that's kind of the time frame we're talking about with the regulators, is where we're going to be in about 8 years from now. So a couple of points on top of the ones that I just made. So something we've been telling the regulators is we're actually looking at something that hasn't ever happened before, which is this inversion of the speed of the air interface relative to the speed of the WAN connection, right? Gigabit connections are available very inexpensively now to a premise, right? It's very different from when I was first on the internet, right, and the NSFnet backbone was running, had just been upgraded to T1, right? We've come a long way. And so we're actually looking at a scenario where if you're running a Wi-Fi AP, even an AC AP in a 20 megahertz configuration, right, you could have a slower air interface than you've got availability on the uplink. I've already alluded to 4G coax, and with 5G, we want to make sure. So there's about a gigahertz of spectrum in play for 5G. So broadly speaking, the 3 gigahertz band has been targeted for 5G across the world. Varies a little bit from country to country. So we need to make sure that Wi-Fi and unlicensed technologies have parity, right, so that we can maintain our role in that ecosystem and ensure that consumers and enterprises continue to have choice. And the bottom line is the WFA forecast, depending on the scenario, somewhere between 500 megahertz and 1.6 gigahertz of mid-band spectrum. And of course, the mid-band is not that big, right? If the mid-band, if you define it as from, let's say, 2 gigahertz up to 7 gigahertz, right, that's a massive chunk of that region. So where do we look for it? So this is going to be a little bit of an eye chart, but I wanted to just give you some sense of what's out there already. And we didn't just get to 6 because it's next to 5, right? It's sort of the punchline of this slide. The regulators were very clear that we had to have a very specific, we need to do all the homework and look at all the options. So this is a view from the top of the 2.4 band to the bottom of the Uni 1 band. of what's there, and the flags on the left, so US, Europe, and then I've highlighted some allocations for the 4G and 5G systems. And the black bars are really probably the most important here. The black bars are DoD restricted bands. And I think everyone can agree that we don't want a repeat of the radar experience again. Can I? So if it's avoidable, right? I mean, obviously we've been through it once. We developed the coexistence technology. If there were no other option, we would figure it out. But our first choice would be a non-DoD, a non-black band, if you will. But just because the band is not black doesn't mean that it's not in use by DoD and that the NTIA doesn't have an interest in it. And that's what the gray bands are. And the dashed red boxes are the number of 160 megahertz channels that could be found in those gaps, if you will. So not very much to look at from that perspective. And then, of course, from a harmonization perspective, Europe is, it complicates the lower part of the band. And then, as I said, in the middle, we have 3 gigahertz mostly allocated for 5G services. So it's not looking good in there. If we look above the top of the Uni 4 band, right, which is not available, but if we just go north, so if we did a study and we looked at everything between there and 12.7, and long story short, there's this very conveniently located block that's non-DoD federal restricted, that is globally harmonized for reasons we'll get into, and you could get potentially 860 meg channels there. So this is how some of the homework that we did to get to 6 gigahertz. So here's what's under study right now, and I've put the current draft channel plan, and this is subject to change. We're still playing around with where the band edges need to be, and of course there are users on either side as well as in the middle. But just to sort of put a point on it, 1.2 gigahertz of spectrum is in play in the United States. And this was basically the subject of the NPRM that came out earlier this month, and it'll be voted on the 23rd. In Europe, we don't have quite so much, but they are actively studying it. So there's 500 megahertz in play. We tried to take it up to 6,700, but we were not successful in that. But it's still 6 more 80s. Right, in Europe. So we're talking about, I mean, this is, if you just think about the amount of spectrum we have now, right, about 580 megahertz in the US, right, this will dramatically alter the efficacy of wider channels and make it so that you don't have to defeature these products coming out of the box. So a little bit about who's in the band. So these are all terms that you're going to start to get very familiar with now that we're in a rulemaking phase. Unfortunately, this is going to add another inch to the CWNA book, I think, before we're done. And by the way, my plug, thank you, Mr. Coleman and Westcott, for writing the AX chapter in the new book. So I know it's not part of the exam objectives, but it's incredibly timely. So in this band, and you're gonna see a lot of band charts from me over the next few slides, so just strap in. But as a level set, the key services in this band, and these are allocated at a global level by the ITU, which is a United Nations agency that has treaty relationships with all the UN countries. So the fixed service, those are the big dishes you see up on towers, and that's basically fixed microwave or point-to-point. Then you have a couple varieties of the mobile service, and we'll get into applications here, but that's anything that's on wheels, effectively, or that flies. And then we have fixed satellite in the band, and then we have what's called the satellite digital audio radio service. So if your car has a Sirius XM in it, for example, there's an XM allocation in the band. So those are the services, what FCC calls, so just like Part 15 or unlicensed is a service, right, or mobile telephony is a service, that's how the regulators think of it. On the top, we now have the users or operators of networks with those services, and this is not complete, but just to highlight, the big one that's not on here, as I'll talk about in a minute, is what they call common carriers, so that's AT&T, Verizon, and so on. So this is the principal backhaul band for links that have not transitioned to fiber in the US. But you have utilities, so we're getting a lot of opposition. So if you look at who's filing in the proceeding, right? It's utilities talking about how the nuclear power plants are going to, melt down if Wi-Fi comes into the band. We have aerial and mobile ground operations for public safety, which is obviously life critical and very important services, but it's also heavily used by broadcasters in certain segments of the band. Railroads, this is used for network control and so on. Financial services is here as well. If any of you read Michael Lewis' The Big Short book, it talks about high-frequency trading. So there's no fewer than a dozen private microwave networks between Chicago and New York City, and that's how they're getting a couple hundred milliseconds to front run the rest of the market, is they're arbitraging the speed, basically, of the air versus the refractive index of glass. So a lot of interesting incumbents in the band, but broadly speaking, this is the structure, and you can get used to it. We're very pleased that the FCC has now adopted the UNI 5, 6, 7, and 8 terminology in their proceeding. So now that you've got a little bit of groundwork, I warned you there were going to be a bunch of these kinds of charts, and I'm not going to linger on this. The presentation will be available, and you can go through it at your leisure, but this is a little bit about how, I'm going to show you a number of different views of this band because it's important that you understand effectively who the incumbents are, and to some extent, I'll say opposition, but I mean, these are, it is by definition an adversarial process because no one wants to give up their spectrum. But we're also working very closely as industry with many of these key constituencies to try to accommodate their concerns. And much in the same way that, say, DFS was developed in collaboration with the defense community and the radar community, we are working with many of these incumbents now. So, but that said, they are obligated to oppose us in the proceeding, right? The big block on the left, effectively, it's exclusively a fixed band, and LTTS is just another version of the fixed service. Then you have these blocks of 4, the narrow band in the middle. That's an exclusively mobile band. That'll be UNI 6. And you'll get more from me on that in a minute. And then UNI 7 is, again, exclusively a fixed band with a little notch for radio astronomy in this kind of that little blob there. And then on the far right, this is a fixed and mobile band. And the reason I'm calling out fixed and mobile is that mobile has some unique problems for us in terms of how we're going to protect. Like, how do we know that there's a TV truck nearby or there's a police helicopter overhead? Right, that obviously is something we have to protect. So how do we deal with it? And then you'll notice on the bottom another interesting thing I didn't mention before is that this whole band actually has a Part 15 allocation already. For those of you that don't know what that means, Part 15 is the federal rules under which Wi-Fi operates. It's the unlicensed rule part. But it's at very low power, and it's for ultra-wideband devices. But this is incredibly important because we don't have to go get a part written for this band. It's a matter of modifying the rules that are already there. So just another reason why there's just this, it's incredibly convenient that 6 gigahertz is here. So let me tell you a little bit more about some of these incumbents. So first, with respect to the fixed satellite service, so just to give you some background, again, terminology you're going to get exposed to over the coming years. So there's a thing called the GeoArc, FSS, again, fixed satellite service, and basically this is a band around the equator where the geostationary satellites are parked, and I'll show you a map of those in just a second. But basically, they're all within a few degrees of the equator. There's some very well specific defined orbits. They're over 30,000 over 30,000 kilometers, actually 42,000 kilometers, 24,000 miles above the surface, and they have a variety of different beam configurations. So they have hemispheric beams that go literally from pole to pole, and then they have spot beams that light up particular countries or regions of countries. And the problem that they're concerned about is aggregate interference. So what they're not worried about one particular link here or there. They're worried about multiple billion RLAN devices that are within the field of view on the lower right corner, right? And what is the collective interference of all of those devices generating? And believe it or not, it is something that at sufficient power could be detected at that elevation. And we're going through that argument with the non-geostationary band now with Globalstar. So here's just a quick map. You can Google all this, or it's in the presentation. But this is a Boeing chart of all the geosynchronous, geostationary satellites around the equator. So there's quite a few of them. And so again, this is we're coming at this from a global perspective. The companies, and it's not just Aruba. There are 12 different companies in our coalition. We're working with Apple, Facebook, Google, Qualcomm, Broadcom, Intel, Cisco, Ruckus, because this is an industry level issue, right? And it really takes a village to get this done. So there is something very interesting going on, which is that what's called the C-band, which is this key satellite band, is being re-architected. As I've said before, the 3 gigahertz band is being allocated for 5G, and that's actually really good for us if it's 6, because these bands are paired. So the 3 gigahertz band is basically a downlink band. That's all the dishes you see around. That's the receive side. But the uplink side is in the 6 gigahertz band, and there's a different NPRM underway right now to reallocate that portions of that band for cellular telephony. Well, if it doesn't need to come down, then it doesn't need to go up, right? So again, part of the reason why just this moment in time is a really important one. So that's a little bit about satellite. Let's talk about the terrestrial microwave service, and this is really the one that's going to probably affect you most from a day-to-day perspective once we're actually able to start shipping equipment. So this is a couple of interesting charts from an opposition filing, actually, but it does so ComSearch is a database company that provides coordination services to microwave licensees in the US. You can see there are somewhere around 40,000 what they call paths. A path could be more than one link, or it could be a single link, and then you can have more than one frequency on a path, right? You can have multiple radios or channels defined on a path. So that's the reason why the numbers are different. So about 100,000, give or take, discrete links or radio pairs in the US, and they talk about the lower 6 and the upper 6. The lower 6 is below 6425, the upper 6 is north of that. So it's a heavily deployed band. You can see there's a lot of it in rural, there are a lot of transcontinental type of links, but there's also a lot of dense urban. Here's a different view of it in terms of who's actually deployed. So again, you can kind of see, you've got kind of the Uni 5, 6, 7, 8 structure in your head, so you can just kind of project that on these different color groups. So on the left, the blue, orange, gray, that's Uni 5. And you can see that that's common carrier, right, is about half the links in the band. And then the industrial business pool and public safety is the other half, give or take. And then there's this notch in the middle that's Uni 6, that's an exclusively mobile band. So that's going to be public safety and broadcast. That's why you see the colors change. And then Uni 7, again, that's a exclusively fixed band. So we're back to the 3 incumbents from the left. And then on the right is a combination of fixed and mobile. So, but the fixed tends to mostly be operated by the broadcast and public safety community. So that's why you see that color banding there. So again, you can start to see the reasons why we drew the 5, 6, 7 breaks where we did, and the basic reason is that we want to make sure that the mitigations or the rule environments are adapted to each incumbent, because we have to protect them, all of those users. But we want to. There are commonalities in how that gets done. Just a little further breakdown within each of those categories, and I know this is starting to be a lot of detail, but just to give you some very specific feeling for who we're up against, right? So on the left, we have the common carriers, right? So Verizon alone has about just shy of 30% of the links in the band in the United States. AT&T, another 21%. So they've been very active, but they've taken, well, AT&T has kind of taken a hard no position in the record. Verizon has expressed more flexibility in their public filings, and we're working with them to try to address their concerns. On the industrial business pool, so we talked about railroads and utilities, but you've also got co-ops, O&G, financial services I mentioned, so about almost 30,000 links there, but no one really big dominant license holder in this case. And then on the public safety side, you can see it's, so there's not really federal here, so it's state and local and agency work, but this is a group that has enormous political power from a DC perspective. So they have they're very active, and of course, it's a crucial service, and it's important that we get the protection right. But at some level, there ultimately the FCC is going to vote to open the band. So like on the 23rd of this month, we're expecting a 4-0 vote to proceed to actually adopt the notice of proposed rulemaking. We're going to go through that process, but at some point in the future, the commission is going to vote again. So it is a technically based process, but it is also a political process. It's just an inescapable reality. Coordination. So this is going to be important for where I end the talk, because we're going to talk, one of the proposals from the industry is basically the new acronym. So you know DFS and the 5 gigahertz band. The new acronym in 6 gigahertz for protection is going to be what's called AFC, or Automated Frequency Coordination. So just park that term, but I want to just kind of ground you in that. So the way it works now is if I want to set up a new 6 gigahertz point-to-point link, I'm required, this is governed under Part 101. Again, remember, we're under Part 15, so Part 101, and there's a couple of others, but govern the fixed service. And I am required to pre-coordinate with any existing license holders that are inside what is affectionately called a keyhole, and you can see the shape there. And basically, the keyhole is defined as an absolute distance in a radius around the receiver, right, that's being protected. The transmitter is irrelevant. It's the receiver that we're interfering with. And then down the bore site of the antenna, because these are very narrow beams, for up to 200 miles down the bore site of the antenna, above 15 gigahertz and 125 miles below 15 gigahertz. So that's the basic requirement, and then you go to a company like a ComSearch, and there are others, and you basically do a technical study that says, okay, here's my equipment, my transmit power, my antenna, and so on, and they do a study that says, okay, you're good or you're not good, and then that report goes in as part of your license application. So that's the coordination process. It's manual. These companies have databases, they use automated tools, but there are people involved in the process. Again, there's only 100,000 links in the band, so you know, you don't have a scalability problem. But if you look at the chart on the right, it leads to these, you know, on paper, very negative outcomes if you said, okay, we want to put Wi-Fi devices, or you're hearing me use this term RLAN because RLAN is short for radio LAN, and this is the term the Europeans actually use, but we're using it for two reasons, because we're working at this at a global level, and so this is a term that the regulators understand, but we're also using it because regulators, this is ultimately not about Wi-Fi. We expect Wi-Fi is going to be probably the heaviest user of the band, but regulators do not allocate spectrum for a specific purpose unless they're selling it. So they're big on what they call technology neutral applications. So we can't say Wi-Fi when we're with, or Bluetooth or any of these technologies. We have to talk about in general terms about the capability of a broadband device, a broadband radio LAN device, if you will. So anyway, if you want to deploy a lot of those devices in the greater Los Angeles or San Diego regions, this one link, right, would be problematic for you, at least in the frequencies that are involved in that link. So how do we protect those links, right, but still enable the scale and the diversity of the Wi-Fi ecosystem to succeed? So hold that thought. We'll come back around to that. Last thought on the fixed service. I know this seems complicated enough already, but anyway, two things to know here. So what I'm showing you now, this is a blow-up of Uni 5. So we're looking at the lower 500 megahertz of the band. So the Wi-Fi channel plan is in green. And again, this may change slightly. It could move 10 megahertz to the right or by the time we're done. But anyway, you can see the 20s, 40s. Look at all those 80s. But on the top, I'm showing two of the fixed service channelizations. So they actually have channelizations all the way down to 400 kilohertz I'm only showing you the 10 and 30 megahertz, which are the most widely deployed channelizations in the band. And you notice that they don't line up very well with Wi-Fi because we're in units of 20, right? And so, and also the blue and the red, these are typically FDD technologies. For those of you who don't know what that means, it means that there's two frequencies. There's an upper and a lower, or there's a go and a return channel. So they're able to do full duplex communication. But this presents a problem from a protection perspective, because how do if I'm under a tower and only one side of the link is transmitting, how do I know what the other side is, right? So this is a technical challenge that we have to overcome, as opposed to TDD, time domain division, which is how Wi-Fi works, right, where everything is on one channel, so that makes it easier to detect. So we've got a couple of issues there, even beyond the actual nature of the incumbents themselves. Let's see, one last slide. This is, can we advance? The clicker is not reaching. There we go. Okay. Sorry, there was one other slide on this. So the next thing is these links actually intersect a lot of places where you could have Wi-Fi devices. And so again, this is a slide from an opposition filing, just to also give you some sense of the other side of the argument, but it makes the point pretty well. So this is a real link. It's about 7.5 kilometers in Manhattan. And the point that they're making in the filing is that there are skyscrapers or high-rise buildings in the main beam of this antenna. And this beam is, of course, three-dimensional. They're showing a 2D cut, but it actually would be as large vertically as it is horizontally here. And so if you're a Wi-Fi device in a balcony, right, or in the window of one of these apartment buildings, their argument is, well, we can't possibly allow Wi-Fi devices into the band because this is going to happen all the time and it's going to blow our links up, right? And so, again, our obligation as industry is to come up with a technical solution that will actually protect this very real situation. Of course, we're also free to argue that this doesn't happen very much, and we've presented evidence and quantitative studies about what the rate of occurrence of this actually is. So while it is greater than 0, it is not very much greater than 0. All right, so we'll take a break from the band plan, but hopefully everybody's kind of level set there. So now let me explain the regulatory and political process that we are going through. And there we are. Okay, so global regulatory action timeline. So I'm going to just walk you through kind of what, again, I said at the beginning that it takes typically up to an average of 9 years to open a band. So settle in. These products are not coming tomorrow. But we're hoping that you might be able to have the first 6 gigahertz available equipment in the United States in time for AX Wave 2. So that would be about 2 years from now. That's the best case. It could get worse than that. But anyway, we had a very successful 2017. The coalition I just told you about, we formed early in the year. We were able to complete the FCC decided to proceed on its own initiative with a notice of inquiry, so we didn't have to file a petition. Excuse me. I'll show you that on the next slide. Also, the European Commission voted to initiate a study item, and it's an EC mandate, so they have no choice in the matter, which is good because, again, it's a political process. So this indicates that there is political will in the European community to actually allocate spectrum for unlicensed. And then we, at an industry level, we got the AX PAR, which is the project authorization request, modified. It was originally defined up to 6 gigahertz, and so of course we had to revise it to go up to 7125. So that was 2017. So to bring you up to the current time frame, you can advance for it. Yeah, thank you. So we introduced a sharing study in the beginning part of the year, and I'm going to show you just some quick highlights from that in a minute. In Europe, this group called SE45, and I'm going to show you a really painful chart here in 2 slides, just to give you some sense of just the insanity that is European regulatory process. But that is underway now. And then the NPRM, literally, I'm thrilled to be able to tell you that the item is out, and you're welcome. You can read it. It's available now. That'll be voted on on the 23rd. It takes about 2 to 3 weeks to be published, and then a 60-day clock begins for the reply phase. And if you can advance the slide for me. Thank you. So the NPRM replies, so there's about 90 days of comment, and then there's a rebuttal round, right? So 60 days for comments, 30 days for replies, so that'll be complete in February. And then, again, best case, if we succeed in making our argument, the first report and order from the Commission could come as early as late next year, or probably more likely the first quarter or first half of 2020. On the European side, there are 2 reports that are due. There's Report A, Report B. Report A is the Coexistence study that doesn't focus on actually how we're going to do the protection. It's just can we exist in the band side by side. So that there's a draft report that's due in a couple of months, and then the principal sharing study will be due in May. And then we expect that the harmonized standard, which is those are the rules that govern how products are certified, that work will begin towards the second half of the year. And then as we roll into 2020, great. So it is likely, for reasons I'll explain, that there's going to be a second round, and that's because of the automated frequency coordination process. We think just because it's going to involve a spectrum database, just to give you the punchline in advance. Spectrum databases typically take time to work out the details. We think it's going to go a lot faster than CBRS did, or TV Whitespace, because we can build on a lot of that work. But we think it's still probably a second trip through the Commission. And then, as I said a minute ago, we're hoping that AX Wave 2 products will ship with the first spectrum that's made available in the US in that initial report and order. So you can imagine, if the AX Wave 1 products are starting to ship here in the next couple of months, the Wave 2 products are 2-ish years out. And I can assure you they're already, all the vendors from the silicon community all the way to the enterprise vendors, we're already hard at work designing how we're going to incorporate this into the products. On the European side, we've got a couple more reports, so just, it's a long process. And then we're hoping for a second report and order from the Commission in 2021 that would be the final rulemaking in the band, and at that time the Europeans would open it as well, and so we begin to ship product into those countries. So that's a little bit about the process. I'm not going to spend a lot of time on this, but for those of you that want to learn more about this, the FCC has a specific defined procedure. You can see the little "We Are Here" thing on the left, which is awesome. So we got through. We spent basically a year and a half to get through the top box. You can see that there is a feedback loop in the bottom, so you can make multiple trips down the slide to get to an RNO, and then the rules are published. In Europe, as I mentioned, so the number of organizations and agencies that are involved is really sort of mind-blowing, and I don't want you to memorize this. The point of this slide is that it's an incredibly complex mess, which is why we call it a spaghetti chart. But these are all, each of these is a different group that has some jurisdiction or responsibility for part of the process. So the technical work is going on in this group called SE45. That's paired with a regulatory group called FM57, and you're welcome to have your eyes glaze over at this point. Those, basically the work product, those are the groups that are producing these reports that then will ultimately percolate back to the Commission. But even once that's done, we're not finished, because before you can import product into the market, there has to be this harmonized standard. So the Wi-Fi products we ship today into Europe, for example, and this is not just Wi-Fi, this is anything with a radio in it, has to conform to a harmonized standard. It has to go to a test lab. We have to produce test reports, right, that show that we comply in all respects. So ETSI is the group that does that, and that work can't begin until the stuff on the left is done. So we got to be in a lot of places, and of course we're also dealing with 28 administrations, right? In the EU, plus another 20 administrations beyond those in the broader European postal and telecommunication community. So it's a ton of work, but again, one of the great things about coming together with HPE, I'll just tell you, because I'm in my 12th year with Aruba, and you know, we never had time or the resources to really focus on this kind of stuff that we've been talking about, and one of the great things about coming into HPE is that we have a government affairs, corporate affairs team that we've been able to sort of leverage for this and kind of show you the ropes, and we've been making investments in people, and I've hired a team that now leads this for me. So, you know, but it's hard to do this unless you have a certain amount of scale because it's a global process. So, since we're all engineers, let's take a quick break. Now you've got a pretty good handle on the regulatory bit. Now let's talk technology. And before we put in all this work, we wanted to have some idea. Okay, so we know the band; it's not federal restricted. We know it looks like it's a lot of spectrum if we could get it. We know those incumbents have a lot of power and they're everywhere. So do we really think it can work, right? So about 2 years ago, we started taking field measurements. We conducted a campaign. And just to give you some sense, and again, you don't have to remember every detail. Again, I'm just trying to give you a peek behind the curtain here of all the work that goes into this, because literally, just repeat myself, but this kind of thing only happens every 20 or 30 years. So it's we are paving the way for we're zoning the next area for Wi-Fi, that'll take us through probably 2040, honestly. Anyway, so we did a statistical sampling. We took a 5.5 square mile by 5.5 by 5.5 mile grid in the Bay Area. In that area, there are 85 different links in the FCC licensing database that either fly over, land in, or launch out of that space. And each of these push pins is a place that we took measurements. We measured at 2 elevations, 2 meters and 10 meters, because we're trying to analyze the clutter field. So the basic goal of this is, we know there's a lot of links here. Can we pick any of them up, right? If we can, that's really bad, right? Because it means that the clutter environment is not helpful, and it means that the quality of the antennas that these incumbents are using is not very good. But if we can't detect them, or we can't detect very much of them, that's probably a pretty good leading indicator that this could work. So we took a calibrated spectrum analyzer. We hired a company to go out and take measurements for us. So this is a picture of one of the setups. They were doing a 10-meter test. Again, it's just all lab quality equipment, because we wanted the measurements to stand up if we ever turned it into a filing. And this is the result. And basically, the way you read this is black is good. So you probably can't read the signal levels, but basically black is below detection threshold, and then the different colors are obviously a hotter signal length. So I'm showing the blue lines are the paths of the microwave links that are in the database, and you can see that we get a few hints of it as we get higher up, and that's absolutely expected. But at 2 meters, basically vehicle level, right, or pedestrian level, we only had one pickup in the range. So the clutter field is pretty effective. Here's a link. This is actually the worst case. I could show you many, many pages of these charts, but this was actually the worst case chart. This link, the collection of points that we chose, which were not coincidental, by the way, we were able to get this link at a pretty good value, which does tell us that we do need to be concerned about coordination, right? So this is not a theoretical concern, but as soon as you get outside the main beam, it rolls off very quickly. We also studied, I said that links, so those are links that were flying over. We also studied links that launched inside this grid. So so this is a particular transmitter, and you could see that we went at different distances in front of the transmitter down the antenna bore site, and then we went off to the side, and we went behind it. And we also tested a couple off-axis measurements as well, because again, we didn't know what we were going to find. And the good news is that it really was only detectable, even in the bore site, at very short range. So this is, again, we've done many, many measurements. I'm just giving you a little bit of a taste for what's out there. But these were the kinds of gates that we all had to get through as a coalition to say, okay, it's worth continuing to invest in this and fly people to meetings around the world and produce the sharing study. So earlier in 2018, in January, we released a compatibility or sharing study. This is a mandatory step. Anytime anybody wants to go open a band, you have to produce a study. So much like the coordination process we talked about, where if I want to put a link in a band, I have to go talk to CommScope, and they're going to analyze my parameters and tell me if I'm okay. If I want a whole band, I have to come in with evidence that says that I'm not going to cause a problem for all the incumbents that are there, who, by the way, are licensees. They are primary users of the band. So we spent about a year and a significant amount of money as a group. We did the biggest sharing study that's ever been done for unlicensed devices. We simulated effectively 1 billion RLAN devices in the continental United States. It wasn't, now not all of those are transmitting at any point in time, and I'll walk you through that in the next slide. We had 3 basic findings. So we found that the interference, and these are just slides from what we showed the commission, but we found that interference into the fixed satellite service, so that aggregate interference problem we talked about with the satellite 24,000 miles up, that basically if you add up 1 billion RLAN devices that were almost 22 dB below the noise floor. I over N is interference over noise. So we're 22 dB under the noise floor from the perspective of the satellite that high up. The second finding is that with respect to the fixed service, again, we have multiple incumbents we have to deal with, we found that 99.8% of all those 100,000 receivers had interference 6 dB below the noise floor or better, and that in no case, even for the 0.2% that was above, in no case did we affect the availability or the operation of the link. And this is really important because these links are designed, again, they're backhaul links, they're, again, utilities, nuclear power plants, railroads. They're designed to have significant extra margin in those links to deal with fading conditions and other kinds of things that happen in the fixed service community. And so that is one of the essential aspects of this band that actually makes it ripe for sharing, is that they have basically a cushion that they can ride on. Of course, they would disagree with everything I just said. But and then finally, for the mobile service, again, the helicopters, the police cars, and so on, we found that we did not degrade that service 99% of the time. And for the remaining 1%, meaning there was some geometry, right? The TV truck pulls up next to where we simulated some RLANs. In those cases, existing procedures, if you think about what life must be like for the engineers that drive the TV trucks, right? They're dealing with I mean, the things that we deal with every day, right? I mean, they never know where they're going to have to be and set up. So they got to go park the truck, find a path to their tower, right? And then find a channel that's clean and so on. So they're already doing frequency management every time they go out. And so basically what we found is that to the extent that any interference happens, it would already be covered by existing procedures. So just a couple of high-level aspects of the study, and then we'll go into the proposal. Actually, I'm going to speed up here because I've got about 12 minutes left. So I said about 1 billion RLANs. We then had a model and said, okay, there's 1 billion devices, but they're not all transmitting at the same time, right? Because typically duty cycles are well under 1% on most networks. So we took the Cisco VNI. We extrapolated out. We said, okay, in the busy hour, everybody's at home watching, every man, woman, and child in the US is watching Netflix. That turns out to result in about 400,000 instantaneously transmitting devices at any instant in time. Then we distributed those devices based on the actual geographic density, based on US Census databases. We then had to come up with a power model. So different, some of those transmitters are clients, right? Tablets, phones, whatever. Some are access points. Some are indoors. Some are outdoors, and so on. So we had a whole model where we distributed those in keeping with evidence, and then we had to distribute them in height because we have, people use Wi-Fi devices in tall buildings, in single-family homes, and what have you, everything in between. So we did all those studies. and then we did this random drop of RLAN devices. And I'm showing you a picture from the European study that's underway now because I don't have it for the US. But here is a view of what a random simulated drop looks like. So this is an FS receiver in London, and you can see 150 kilometer. If it's further than 150 kilometers, we ignore it in terms of interference to the receiver. So that's the geography on the left. On the right are all the RLANs that we dropped in the simulator, right, that are co-channel. So in this particular simulation, we're actually doing even more than we did in the US. So there are almost 9,000 co-channel RLANs that were randomly dropped within 150 kilometers of this receiver. And by the way, we dropped almost 23,000 in that area. It's just that 9,000 were co-channel with the frequency of that link. Okay, and therefore would have interference. The others could be disregarded. So that's, when I'm saying random drops, that's what I mean. And then what we do is we add up the power that's being emitted from all these transmitters, and we look at what that does to, what kind of interference does that generate. And here's a close-up view. So the push pins here are just showing you where the RLANs were with respect to these particular FS receivers, and it's proving that the random drop actually does what we say it does. So we looked at it from a satellite, from a terrestrial microwave perspective. Any of you with statistics backgrounds, unfortunately, I don't have a simpler way to present this chart. The important thing is that the big curve is to the left of the red bar. So basically what we found is that only 0.2% of the time do we have an interference level that's above 6 dB below the noise floor. And for those of you that you wouldn't have any reason to know this, but that is a key protection criteria threshold that regulators use. So that's why we measured against that criteria. So basically, we're good as far as the fixed service is concerned. As far as the satellites are concerned, so again, we have to simulate all this energy going up into the sky. Right? And so what we did there was we said we simulated the lower 500 megahertz. That's where most of the satellites are that you can see from the US. We distributed even imaginary satellites. We basically measured interference in 0.1 degree increments around the equator. And again, we dropped almost 1 billion RLANs. And we had two really interesting findings. And again, I don't normally show these charts, but since we're mostly engineers here, I thought you'd appreciate this one. So the top chart is interference that the satellites are already getting today. Remember, there's terrestrial microwave in the band, right? So fixed satellite and terrestrial microwave are co-primary. So the satellites, right, when you have a microwave beam, it keeps on going, right, after the receiver, right? So, right, you got to figure out, for gun safety, right? You think about what's downrange, right? So you can have satellites downrange. And so what this is showing you is that on the left, this is the I over N, this is the interference level relative to the noise floor. And what you can see is that the interference actually spikes to over the oceans, right, over the Atlantic and Pacific, which makes complete sense if you think about I got a bunch of satellites parked over there, and I'm illuminating them with my high gain 2 degree beam antennas, but it's very light in the center of the country. So they're already getting hammered, is the point. And then if you look at the bottom, this is our simulated Wi-Fi deployment. And there are 24 different channels. That's what's in the middle. And so we had to simulate every single channel because it's a statistical process. And if you just compare the scales on the upper and lower chart, you see that the Wi-Fi level it's 20 dB below what the fixed service is already generating to those satellites. So we conclude we're in great shape as far as the satellite community is concerned. But again, these are the kinds of things that you have to do, right? These things are multi-billion-dollar assets. Right, they have enormous, and their defense applications, right, broadcast, a lot of people with a lot of money depend on these systems, and so we have an obligation to go through this kind of an exercise. All right, so I'm going to close just to give you a sense of what we've proposed as industry and to explain AFC to you at a super high level. So this chart is showing you on the top what we've proposed to the commission, and the bottom is what we got in the NPRM, and we're working to try to change it. We'll see. We're trying to get some questions sort of added in, as you can see from our public filings. But basically, what we said is we basically advanced two types of devices, indoors and two types outdoors. So indoors, we have this concept called low power. Low in this case, the NPRM talks about 1 watt, or 30 dBm, so that with the antenna. So that'd be 24 dBm conducted plus 6 dBi of antenna gain. And then standard power would be more like the Uni 3, Uni 1, so 4 watts, right, or 36 dBm. At least that's what's in the NPRM. We'll see where we land on low power, but anyway, so we propose that low power class would work just like non-DFS channels today. There'd be no encumbrance whatsoever, and that just being indoors and being at this reduced power level is sufficient to protect the satellites, protect the microwave, protect the TV trucks, and so on. But if you're high power indoor or you're any outdoor operation, and now you have the reason, you can see why we need this, you're going to be subject to something we're calling automatic frequency coordination. So that's that process we talked about before, but scaled up, automated to work for a market that, you know, we shipped over 3 billion chipsets this year. So the system has to work at that kind of scale. And so we said, okay, we're going to have those 3 devices, those 3 classes subject to AFC. So what we got instead was 2 bands with indoor low power and 2 bands with AFC, and it's kind of a checkerboard configuration. We disagree with this, and we're looking forward to arguing our case here in the NPRM. We think low power is safe across the band. We intentionally did not go for AFC in Uni 6 because of those mobile operations, and it's a fight we don't need to have today. You know, again, we think low power indoor is enough in that band. So the basic decision tree is, you know, what device type am I? This is our proposal, right? If I'm a client, I operate under control of an access point, so end of story. If I'm what we call a master, right, then am I outdoors or indoors? If I'm outdoors, right away I need AFC. If I'm indoors and I'm a higher power, I need AFC. If I'm low power, I can just fire up and start transmitting. So that's the basic structure. So what is AFC? It's basically a coordination system that ensures that a Wi-Fi device does not transmit in a channel that's going to create interference for an incumbent. So that means I have to know where I am. And so there'll have to be a location, basically 6 gigahertz capable devices that are not low power will have to have a geolocation capability, which is good for a whole lot of different reasons. Now that could be done a whole bunch of ways, as I'll talk about in a minute, but that's step 1. Step 2 is I have to check in with a database before I begin transmitting, and then periodically thereafter, and you know, we haven't put something into the record about how often that should happen, but it would, you know, we're thinking on the order of days or weeks, not minutes or hours. And then we get a list of available channels. The clients have to, you know, to operate under control of the master, so the peer-to-peer operation would be constrained in this band. And from a location perspective, whereas in CBRS you have this, you have a fixed location accuracy requirement. Again, if you think about Wi-Fi, right, we have so many different kinds of devices and price points and business models. So we want to, our message to regulators is we want a simple rule model that says, okay, these are the rules to protect incumbents, but within that framework, anybody should be free to implement whatever business model works for them. So you could have GPS in the access point. You could have a service provider provisioning in a street address in a control system. You could have you could be getting location from smartphones, like a professional installation application, so on. Whatever, as long as it can be certified and shown that it complies with the rules, it should be permitted. And then this is a little bit about how the actual system will work. So again, in the upper section there, I'm just showing APs that are standalone, and in the bottom, more of a managed deployment with a controller. So AFC operator is the term we're using. That would be equivalent to the SAS concept in CBRS or the TV whitespace database, but much simpler than in those bands. And then and you could have a controller that's sort of proxying. And then, of course, you have to have the location detection capability, and they are getting updated from ULS. So that's basically the system that's coming. This is the one that's going to probably take a second rulemaking, because what we want to get is we want indoor low power as fast as we can get it. And those are the products that'll ship. So the bands that those are opened up for, that's what we'll catch the AX Wave 2 wave for. And then if we need more time to get the AFC exactly right, that we'll take it, and then the next wave of products would have AFC enabled. But anyway, I know that's a ton of material. I think I'm almost out of time, but I'm happy to take a couple of questions if Tom can give me a couple of minutes here. So if we bring the lights up. Oh. Robert said people are still ingesting. All right, so I'll be around for a little bit afterwards. Thank you very much. I'm pleased to be able to tell you about this, and enjoy the rest of the conference. Thank you.